Alright, AP Physics 2, Unit 3, Lesson A, the second part of the multiple choice. There are going to be four, it looks like, parts to this. This is numbers 16, 18, 21, 23, 30, 32, 33, 38, 39, and 40. Let's get started. Let EA be the magnitude of the electric field produced by sphere A near the location of sphere B. And let EB be the magnitude of the electric field produced by B near the location of A. So just the fields at those locations, so not the actual forces. Which of the following correctly ranks E, A, and EB? You know what? I don't really get the feeling that there's a diagram missing in this one. Let me go take a look. 1 second. I'm going to pause my recording. Yes, I was right. There was a missing diagram. So here we go. We now have our diagram. So they're saying, just to label this thing correctly here, they're saying that EA is the electric field at this location. Now remember, that does not require B to be there at all. We're just talking about the electric field at this location where B is. And EB is the electric field by B at this location. But once again, when we're considering the electric fields, we're going to ignore the charge that is at that location, because the field is created by the other charge in that location. Now, the charge on A is 10 microcoulombs, and the charge on B is 20 microcoulombs. Okay, they want to know which field is bigger, the B's field here at A or A's field here at B. The fields, while the forces they're going to feel are the same, Newton's third law says the forces have to be the same. The field strengths are not. B's field is going to be larger than A's, but it's going to act on a smaller charge when we do consider force, or if we do consider force. And therefore the forces will come out to be the same. In fact, B's field is twice as strong here at A as A's field is at B's location. So EA is less than EB. So that goes back to either this one. Really, it's only one, because it's just this option here, because the electric field by A, which has less charge. So I would go with A in this case. I'm going to double check my answer because I don't want to lead you astray. But 16, yeah, it should be A, so I'm right. Let's look at their reasoning. Because the same distance away from the point charge, a larger magnitude charge will produce a larger magnitude electric field. So remember, electric field is K, charge that creates the field, divided by the distance between the location that you're considering and the charge. Well, in this case, this is the same for both. QB, charge B, has the bigger charge, so it's going to have the bigger field. This one we should probably save till later until we know what a, yeah, let's skip this one until we get to some modern physics under our belt. We'll learn that stuff about alpha particles and all that, but we'll come back to that. 21. Which of the following best describes the location of a point, other than at infinity, at which the net electric field created by the two charges will be 0? Alright, so in the middle, I think we can rule out anything in region 2. Because if I'm a positive charge, I'm being attracted this way, and I'm being repelled this way. So there's no way they can cancel. We've got to find a place where the two are at least against each other. Alright, so let's see. On this side, 2, the charge by the 2q is going to be very large. We'll call that the green charge, because you're really close to it. The charge by this single charge, it's far away and it's less, is always going to be less than this. So I don't see them being able to cancel here. But if we go over here in region 1, Q2, the charge by 2q over here, could be relatively small because I'm far away from 2q. But since I'm close to the smaller charge, it may be able to muster up enough oomph to cancel out. Except I think I have them reversed. Yes. The red one would go this way, and the green would actually be this way. There we go. Repulsive, right? That'd be the field. So the field would be repelling, it would be positive. Yep. So I would say region 1. Charge positive Q is placed at the center of a hollow metal sphere in the cross section above. The net charge on the sphere is 0. What are the induced, the charge on the sphere is 0. What are the induced charges on the inner and outer surface of the sphere? Well, if you put a charge in the center of a metal sphere, I would assume that the negatives will gravitate, so to speak, will be attracted towards the inner surface, and the positives will be attracted or be repelled to the outer surface. Assuming that they both can move, we know how it really works, but sometimes it's just easier. So, evenly distributed. I would say now the induced charges. I would say, well, I guess based on I'm gonna give my answer, then I'm gonna check the answers to see if I'm right. Let's see. So I mean, based on what I've said so far, you'd have to say the inner surface was negative Q, and the outer surface was positive Q. I'd say C. Now, am I right? Let's check. I'm not 100% sure on this one. 23. C. Okay, I am correct. That's a tricky one though. That can be tricky. The positive charge here on the outer surface would be spread out more from each other because there's more surface area to work with, but the total charge would be the same. Some students experimenting with an uncharged metal sphere shouldn't play with that kind of stuff. Come on, kids. I'm just kidding. It's just a metal ball. Want to give the sphere a net charge using a charged aluminum pie plate. Well, that's awfully specific. I don't really... Anyway. Which of the following steps would give the sphere a net charge the same sign as the pie plate? If you want to do the same sign, in my thought, you're going to have to touch the two. So if you take the metal sphere and you insulate it from everything, so you put it on some kind of a plastic rod, and you now it's a net charge using... Yeah, and if you bring this pie plate, side view, pie plate, there we go, up, and it's got, say, positive charge, when you touch it, some of its positive will come over here, and then if you remove it, so contact would work. Let's see. Bring the pie plate close to, but not touching. Bringing the pie plate close to. I would just go with D, touching the pie plate to it. That should do it. Everything else is induction and is going to charge at the opposite sign that you want. Yeah, all these others are floating with induction. Like if you connect a grounding wire or whatever. Let's go through real quick. If you do A, nothing happens to the metal sphere. When you leave, it's the same. If you do B, the positives, when you touch the grounding wire, these extra positives, so if you don't touch them, but the positives will flee away, leaving the sphere negatively charged, which is the opposite of what you wanted. C is just going to discharge the metal plate and leave everybody not charged. So, yeah, D is your best option. It's charging by contact. An isolated hollow aluminum sphere is positively charged. A cross-section through the center of the, I'm assuming, sphere. Is this all we have? Yeah. The direction of the electric field is correctly indicated in which of the following? Alright, the sphere is positively charged? Yes. So, first of all, inside the sphere, it's going to be 0. So, B, C, and D, 0. A is going to be, and A and E are both going to be in directions that are away from the sphere, because the electric field will point in the direction a positive test charge would go, and it would be repelled by a positive sphere. So E's field should be to the right, A's should be to the left, and there should be 0 here for those. So I'm going to cross out this. To the left at point A, to the right at point E. I would go with that. I would go with 1 and 3. 32, yes. Magnitude of the electric field is going to be greatest at A, closest to the surface. Inside 0, but as soon as you cross over, you're in that area of the maximum. And if I may be, here's a little indicator of that. If we go all the way back to the previous video, there was a question that looked like this. Notice, while you're inside the sphere, it was 0. As soon as you got to the outer part of the sphere, it was at its maximum. As you get away from the sphere, it's going to only go down. So the maximum electric field strength is going to be right at the surface of the sphere. Now I have to find the page I was just left. I'm pretty good, not going to lie. That's pretty good. Alright, so should be at A. 38. The four charged particles shown above are held at fixed corners of a square. The electric field at point P is directed. Okay, so let's do this. So we're going to label these things different colors. Red, green, blue, black. Alright. So let's just do the field one at a time. For the black, it's going to be pushed away 1 unit, like that. For the red, it's going to be pulled toward, the field's going to be directed, it's going to be directed towards there, 1 unit. For the green, it's going to be directed towards 1 unit, so it's also going to be in this direction, same as the black. And for the blue, it's going to be directed away from the blue, so it's going to be this way. So really you end up with 2 vectors going that way, 2 90 degrees to it that way. When you add them, you should get something going straight up. So I would say towards the top of the page. Three identical conducting spheres, 1, 2, and 3, are mounted on insulating stands and placed as shown above. Spheres 1 and 2 are each uncharged, and 3 carries this positive charge. Spheres 1 and 2 are connected to each other with a conducting wire that they don't show. All right. After the wire is removed, sphere 3 is moved far away. Which of the following statements about the charge is okay? So, while they're connected by a wire, if you have a positive charge here, negatives are going to build on this, and positives are going to be move over to the other side of this. If you cut the wire and then remove 3, is that what happens? The wire is removed, then sphere 3 is, then you're going to have a positive charge on 1 and a negative charge on 2. And they should be the same size spheres, so they have the same amount of charge. Equal, no, not positive. Sphere 1 is positively charged and sphere 2 is negatively charged. That's the one we want. Hollow metal sphere is shown above is positively charged. Point C is at the center of the sphere, and point P is any other point within the sphere. Which of the following is true about the electric field at these points? They're both 0. Anywhere inside is 0. Anywhere inside a conducting link is 0. Alright, that endeth the second part video.